Hey everybody, Dr. A here, and in this video we're going to be providing an introduction to material properties. Now, this is a topic that we typically dive into in a mechanics of materials course and probably even further in like a structural analysis course or soil mechanics course even. But for the purposes of this video, this is just meant to give you a brief introduction to material properties. And so this would be a really nice introductory piece of material or intro video for a statics course or even a dynamics course. So let's go ahead and jump into it. What are material properties? Well, material properties are aspects of every material that describe how those materials behave when loaded. Now, different material properties enable us to compute member deformations and ultimately help engineers predict how a material or an element or a system may fail due to loading. So maybe pause the video and write this down and really understand what these couple of sentences are saying. We're talking about materials that have certain properties, and those properties, those numerical properties, those aspects of different materials help engineers determine how those materials are going to behave, how they're going to deform, and ultimately how they could fail whenever you apply a load to it. So let's look at a couple of kind of simple illustrations, okay? Let's say that you have a beam here, all right? And, it could be any kind of beam. For example, we could make it a cantilever beam, and let's say you have a cantilever beam and you have some applied loading here, P. Now, if we're interested in how this cantilever beam will deflect, so for example, if we load this beam and we know that it's going to deflect something like this, okay, a little bit of an exaggeration, but deflect something like this. Now, if we want to get information about this deflected shape right here, or if we want information about this amount of deflection, I'm going to call it delta, we're going to need to know something about the material that the beam itself is made out of, okay? We'll need to know some information about the material properties of the stuff that the beam is made out of. So for example, if this beam is made of steel, it will deflect a certain amount due to that applied load. If it's made of concrete, it's going to deflect a different amount because concrete is a different material than steel. If it's wood, it will deflect yet again a different amount because wood has different material properties than steel and concrete, so on and so forth, okay? Similarly, what if you have a column, for example? Let's say you have a column here. And, let's say we got some pin connections here. And let's say that column load has an axial force here, P. Now, when you load this column might want to buckle, okay? Let's say this column tends to bow out or buckle like this, okay? So again, how is this column going to buckle? How much is it going to buckle? What is the force that would cause a column to bow out like this? Well, again, the way we compute that behavior, the way we model this buckling or this deformation behavior of a column, similar to what we just talked about with this beam over here, we need to know information about what the column is made out of, what material is the column made out of, and what are some of those properties of that material, because a concrete column and a steel column and a wood column are all going to behave very differently. And then similarly, if we can keep looking at all these different kinds of illustrations, of course, but similarly, let's say I have, a machine component. Let's say I have some kind of like L-shaped bracket here that's, a machine component. And, maybe it's restrained here and maybe it's got some other kind of restraint here. And I want to know if I put a load here on it, if I want to know how much this machine bracket is going to tend to deform like this, and maybe even move over an amount delta. Again, I need to know about what the material that this bracket is made out of. If it's a machine bracket, is it made out of steel? Is it made out of aluminum? Is it made out of copper or brass or bronze? All of these are different materials that have different properties, okay? And depending on what the properties are, it's going to influence the amount and the mechanism by which these things behave when they're loaded, okay? So that's the idea behind material properties and why they're important. Now let's write a few more sentences down. The next sentence we have here says that several material properties can be determined from a material's stress-strain diagram. Now, we probably know a little bit about stress already, right? Stress, we use the Greek letter sigma for stress. Strain, which I'm going to define here in a second, we use the Greek letter epsilon for strain. So it turns out we can relate the stress and the strain in a member or in a specimen and determine different material properties for that material, okay? So let's first review, though, what is stress and what is strain. Well, stress or sigma is a measure of force in a member divided by some area that force acts over, okay? So in general, we can write an equation for stress. Stress equals force over area. And stress is going to have units of course, force over area, right? So that would be force over length squared, all right? So these are units, for example, like newtons per meter squared, which you may remember is a Pascal, or you have pounds per square inch, which is a PSI. We also have kips per square inch, which is a KSI. And there's other examples as well. Okay, so that's the idea of stress. In this playlist, we've defined stress before in some previous videos. Okay, what about strain? Strain is a measure of deformation due to loading within a member. Okay, so more specifically, the equation for strain, we're going to say epsilon, is going to be equal to little delta over L naught, where little delta is a deformation. So that's going to have units of like length, okay? So that would be like inches or millimeters, for example. And L naught is original member or specimen length. Okay, so it turns out epsilon is dimensionless. Okay, so I'm going to say epsilon has units of dimensionless. It would really have units of like length per length, which really just cancels, right? So you can, some people think of strain as doesn't have any units, but it's really better and more accurate to write it as a deformation length, which is like, again, inches divided by the original length, which may also have units of inches, okay? Now, again, this is meant to be introductory material for the purposes of maybe a statics or a dynamics course. If you take a full-blown mechanics of materials course, you're going to dive a lot more deeper into that. And I actually have a playlist for mechanics of materials as well that has a lot more information on this if you want to check that out. Okay, so let's keep going with this intro type of material. So it turns out that if we load a specimen and measure its stress and corresponding strain, we can plot stress versus strain. Now, from this stress-strain plot, we can determine different material properties of that particular material. So, for example, you can have a steel specimen, and you can apply a stress to it, and then it will correspondingly deform or maybe stretch or compress. And from that, we calculate the strain, and then we can plot these together. So if we were to plot stress and strain together and try to relate the two together, it would look something like this. You would have a vertical axis, okay? And that vertical axis will be stress. And then you're also going to have a horizontal axis. And that horizontal axis, that's where you're going to plot strain, okay? Now, for most materials, not all, but most materials, what's going to happen is for the first part of this stress-strain relationship, it's going to be pretty linear, okay? We sometimes call this the linear elastic region, okay? And then what happens is at a certain value of stress and a certain value of strain, you're going to start getting some nonlinear behavior, okay? And then all of a sudden, you're going to have a drastic increase followed by a decrease, and then you're going to have the material fail, okay? And so once again, what this relationship will look like is it's going to be kind of linear at first, then you're going to develop a little nonlinearity, then you're going to have this very nonlinear curved portion here. Okay, now from this plot, this is where we can extract data, extract information on these different material properties. Now, again, for the purposes of this introductory piece of information, I'm not going to dive into it. If you want to check out more details on this, check out my Mechanics of Materials playlist. I have actually several videos that talk about material properties and material behaviors from those properties, okay? But let's hit some of the highlights here, okay? One important material property that's, I would argue, is probably the most important and the one that's the most used in engineering applications is called the modulus of elasticity. And that is actually the slope of this linear portion. And we call that capital E, okay? So I'm going to say E is the modulus of elasticity, okay? It has another word, another name for it. I'm going to say also known as Young's modulus. Okay, Young's modulus or modulus of elasticity. All right, it is the slope of the linear portion of the stress strain diagram. Okay, and guess what units it has? It's going to have the same units as stress. Okay, let's see if I can spell stress right. Stress, okay, which is again force over area. Okay, how do we know it has units of force over area? Well, again, it's a slope, right? And so it's rise over run, all right? So if we rise up by a stress value and we run by a strain value, then we can write this as modulus of elasticity is delta sigma over delta epsilon, right? It's kind of like delta y over delta x from algebra, except it's delta sigma over delta epsilon. Now, remember, what are the units? What are the units of stress again? Stress has units of force over area. And then what does epsilon have units of? Length over length. And so the lengths over length cancels, and you're just left over with force over area as the units of epsilon. I'm sorry, as the units of E, not epsilon. Units of E, which is, again, modulus of elasticity. So that's a really important material property. Another really important material property is the ultimate stress, okay? This is the highest level of stress on this stress strain diagram. I'm going to call this sigma sub u. Another important value here is the failure stress. This is sigma sub f for sigma sub failure, okay? And then another really important property is what's called the yield stress. Now, the yield stress is in the neighborhood of this nonlinear portion right here, where the material just starts to become nonlinear. We're going to call that sigma sub y. So I'm going to write these down real quickly. Sigma sub u is called the ultimate stress. Okay, again, that's the highest point on the stress strain diagram. And then sigma sub f is the stress that causes failure. Again, that's called the failure stress. And then sigma sub y is called the yield stress, okay? This is the stress where the material first begins to yield, which means it first starts succumbing to permanent deformation, okay? So that means that it's going to be permanently deformed pretty much at that yield stress, okay? Now, the way we get this is there's a technique to get this yield stress. It's called the 0.2% offset method, okay? Which I'm not going to talk about this video, but I have a whole nother video in my Mecha Materials playlist that talks about this 0.2% offset method. But again, for the purposes of this video, we just want to kind of briefly give an overview of some basic material properties. Another couple of things I want to talk about with this diagram is that as long as you are within the vicinity of this linear portion, we call this the linear elastic range, okay? And what that means is if you load a member or a specimen and your stress level is within this linear portion, that means that if you unload it, then the material will rebound back to its original shape, which would be zero strain in this diagram. But if you load a member or a specimen beyond its yield point, that means you load it somewhere here in this nonlinear region, that means that even if you were to take the load off, you're going to have a permanent deformation, okay? It might not have failed yet, but it will have some kind of permanent deformation. And the way we can think about this is think about a simple rubber band, right? When we were kids, we would take rubber bands sometimes and we would just stretch them, right? And sometimes we'd play this game where we try to stretch a rubber band. We'd see how far we could stretch it before it actually breaks, okay? So if you stretch a rubber band a little bit and then you let it go, it's going to go back to its original shape. But if you stretch a rubber band a whole lot, but you don't break it, before you break it, you just stretch it really far and then you let it go, it will bounce back, but it's not going to be the exact same shape it was originally. It's going to be a little stretched out. It's going to be a little permanently deformed, okay? And so that's what happens if you load a specimen to the point where you exceed this yield stress and you get into this nonlinear behavior, okay? So again, that's going to conclude this video. This is just meant to give you some background information and a little introduction to material properties. This is meant to be kind of shown to students in a statics or dynamics setting, but if you take a full-blown course in mechanics of materials and structural analysis and soil mechanics and machine design or aerospace material design, for example, you're going to dive into a lot of this information a lot more in depth, okay? So thanks for watching, and please be on the lookout for other content like this, and don't forget to hit like and subscribe.